We've been studying the group of motions, which we determine Rn dot On, group of motions of Rn preserving the distance from between 2 points, sometimes called the Euclidean motion group. Last time we proved, well, we did this for n equal 2, but if you look at the proof, it's exactly the same, that if you have a subgroup of G, which is finite, then gamma fixes a point P, some point P in Rn, so is conjugate to a finite subgroup gamma inside of On, which is the subgroup G0 fixing 0. So if you look for finite subgroups of this motion group, they're actually all determined by the finite subgroups of this subgroup fixing the origin. So the point fixed is this barycenter or center of mass, exactly as it was in the two-dimensional case. The same argument works in the n-dimensional case. So when classification of finite groups of this reduces to the classification of finite groups here, which is an interesting problem and has only been solved in very few small n cases, n equal 2, 3, and 4. So we did last time the finite subgroups in the orthogonal group of dimension 2. And we found out that they were of two types. The first type, 1, was we let gamma plus be equal to the gamma in gamma whose determinant is 1. So the rotations in gamma. So the first type was when gamma was equal to gamma plus, and that was then gamma was cyclic of order n, generated by the rotation of the smallest angle. And the second case was when gamma was contained gamma plus with index 2. So there were elements in gamma of determinant -1, and those groups were dihedral of order 2n, so that this was cyclic of order n. And everything in the non-trivial coset had order 2 and was a reflection. And the reflections conjugated elements of this cyclic subgroup to their inverses. So I could write if cyclic of order n, and that R rotation by theta R inverse is equal to rotation by theta inverse for all R in gamma minus gamma plus. R squared is equal to 1. Now you get a nice picture of these groups if you consider regular n-gons, because they're preserved by these groups. So let me show you how this relates to these finite groups relate to regular n-gons. So one imagines starting a regular n-gon. Let me see if I can draw a regular octagon, maybe. This isn't. No, it's not going to work. What am I drawing here? Let's draw a regular hexagon. Why don't we do a regular hexagon? That I think I may be able to do. This would be the case n equal 6. So if you think of the action of the cyclic group of order 6, it takes this point to that point, because this is a rotation through 60 degrees. That's the rotation of order 6. Theta is as small as possible, so theta would be 2 pi over n, because that would be the rotation that, if you did it n times, would take you back to the identity. So this would be it would take this point to this point, it would take this point to this point. So one orbit of the group would be the vertices of this regular hexagon. But you could also have the dihedral group of order 12 acting on that hexagon, because if you also thought about reflection through the lines that go between the midpoints of the edges, there are 3 such lines that go through the midpoints of the edges. That gives you 3 reflections that preserve the regular hexagon. And you also have the lines that connect the vertices. There are 3 more lines like that. So that gives you 6 lines through which you can take the reflection and preserve this regular hexagon. And those are the 6 elements in the dihedral group of order 12 that are not in the cyclic group of order 6. Now notice they come in 2 different flavors, those type of reflections. There are the 3 ones that connect pairs of opposite vertices. And then there are the 3 that are through the perpendiculars of the opposite sides. And so the 6 reflections in the dihedral group of order 12 really are grouped as 3 plus 3, where these are lines through vertices, and these are lines through the sides. Whereas that happens for the hexagon, if instead we took the triangle, which would be the case of the dihedral group of order 6, this would be n equal 3, dihedral group of order 6, which I said was the same thing as the symmetric group on 3 letters. There, the lines through which you can reflect to preserve this triangle go through a vertex and the opposite side. So there, well, I didn't draw that too brilliantly, but there are 3 lines through which you can reflect and preserve this triangle. And those are the 3 involutions there are 3 elements in gamma minus gamma plus in this case. Those are the 3 elements of order 2 in the symmetric group on 3 letters. And they're all of the same type, 1 vertex, 1 side. And what happens is that in this case, the 3 elements in gamma minus gamma plus are all conjugate, because they're all geometrically similar. Whereas in this case, the 6 elements in gamma minus gamma plus form 2 conjugacy classes, the 3 of this type and then the 3 of this type. And that's a general phenomenon that distinguishes even and odd dihedral groups. When n is odd, we're going to get back to this, the elements in gamma minus gamma plus are all conjugate in gamma. When n is even, in this case, the elements form 2 conjugacy classes. Because you have 2 different types of lines through which you can reflect and preserve the figure, the ones through the edges and the ones through the vertices. Whereas in the odd case, each such line goes through an edge and a vertex. So we'll come back to conjugacy in the dihedral group, but that geometric picture helps you distinguish the even and odd cases. By the way, there's one other dihedral group that we've seen before. The dihedral group of order 6 is the symmetric group on 3 letters. The dihedral group of order 4 is the Klein 4 group. Because the dihedral group of order 4, if you might think of it, the regular n-gon is just a 2-gon. It's kind of stupid. N equals 2. It only has 2 sides. They're right on top of each other. They didn't really separate. They're trying to look like this, one up here and one down there, but they didn't have enough room. And the reflection is this reflection. That's the element in the non-trivial coset, whereas the rotation is the rotation by 180 degrees. And if you think of the group generated by those 2 involutions, they commute with each other, and that's the Klein 4 group. It has 3 involutions in it and the identity element. Whereas all the other dihedral groups, D2n, n greater than or equal to 3, are non-abelian and act on the regular n-gon. Yeah?
So D4 is the permutations of the 2-gon,
not the 4-gon. The D2n acts on the regular n-gon.
Is this the same notation as I?
Is this the same what?
Is this the same notation?
No. I said that last time.
Oh, okay, sorry.
I said that last time. I'm using the notation where D2n, this is the order of the group. And let me clarify that. So that acts on n-gon, and it's what Artin calls dn. Okay? Whereas this one he would call Cn.
So Artin does call that dn.
Yeah, he calls this group dn.
Okay.
So the Klein 4 group for Artin would be d2, and the symmetric group on 3 letters would be d3. By the way, the permutation, the isomorphism between this and the symmetric group on 3 letters is the permutation of this dihedral group on these 3 vertices, or equivalently on the 3 edges. And in general, if you think about it, this d2n, as I have it, is a subgroup of the symmetric group on 2n letters. In fact, on the symmetric group on n letters. Sorry. Because it permutes the vertices of a regular n-gon. But the difference is that when you get n bigger than 3, this group has order 2n, this group has order n factorial, and is a much bigger group. But just in the case when n equals 3, they turn out to be the same. This is acts on vertices. So this notation, it's a matter of choice. I just can't deal with Artin's notation. In general, he chooses brilliant notation, but in this case, I couldn't abide by it. Okay? If you feel better calling it dn, call it dn. Okay, now we're going to get to a much more interesting subject. So this is the classification of finite groups. But in the finite group case, we didn't really need this whole group of motions. We could have just asked for the finite groups or the orthogonal group, because they preserve some point. But today we're going to get into the really interesting subject, which is more general than finite groups. More generally, we want to classify the discrete. And I'm going to say what that means. Subgroups gamma in G. So a discrete subgroup means the following. Remember that elements in G are products of translations and rotations. So everything here, any element G, is uniquely expressed as the product of a translation by a vector times times an element in ON. And that element can be written as either translation by a vector, rotation by an angle. We're just going to go. All right, discrete subgroups. I'll tell you what a discrete subgroup is in G, which is R2, O2. Discrete means that gamma does not contain arbitrarily small rotations or translations. So I have to say what that means. And arbitrarily small means that if it contains a translation by a vector, the size of that vector is bounded from below. And if it contains a rotation, the angle of that rotation is bounded from below, independent of what elements in gamma, i.e., there is an epsilon greater than 0. So that if TB is in gamma, the size of B as a vector is larger than or equal to epsilon. And if rotation by theta is in gamma, the size of theta is bigger than or equal to epsilon. You can't translate by arbitrarily small elements. You can't rotate by arbitrarily small elements. That's because we know basically what things in here look like. What does it mean for something in here to be discrete? Well, we have a notion of what a small element is in ON. Namely, these groups have a notion of distance on them. ON, so an arbitrary element looks like this. We could also ask that gamma not contain arbitrarily small translations. So B is bigger than or equal to epsilon. And A is not too close, arbitrarily close to the identity element, in the sense that the matrix entries of A are not all within epsilon of the matrix entries of the identity element. That's a way of generalizing this rotation is at least a large angle. This is by that I'm saying that this particular transformation, which remember is is cosine theta, sine theta, minus sine theta, cosine theta. To say that theta is greater than or equal to epsilon says that this matrix is not arbitrarily close to the identity element. Because if theta got too small, the sine of theta would get very close to 0, and cosine of theta would become very close to 1. So in general, we can ask that the elements of gamma not be too close to the identity transformation. And the fact that we have a notion of size on real matrices and we have a notion of size on real vectors allows us to make that statement. Now, finite groups have that property. Because finite groups are only a finite number of elements in the group. So you just find what is the smallest angle of rotation involved, what is the smallest distance of translation involved, and that's your epsilon. But the fact is this can exist for infinite groups too. So I'll give you a simple example of an infinite discrete subgroup that isn't finite. An infinite discrete gamma inside of G, Rn, On. Let B be a non-zero vector. Take gamma equal the cyclic group generated by translations in B. So translations have infinite order. If you start at the origin, and here's the vector B, takes your origin up to B, and then if you do it again, you'd go to 2B, and then if you take it again, you go to 3B. And you never get back to the origin because you keep moving further away. And you also have the translations backwards to minus B and to minus 2B, etc. So that's a perfectly good example of an infinite discrete group because it doesn't contain arbitrarily small translations because no translation has distance less than B in it. Now, what we're going to do is classify all possible discrete groups of this group. And that, of course, we have the finite groups, but then we have the groups that have elements of infinite order in them, and we want to find those groups too. And that's a beautiful problem that's related to various, as the book describes, various designs of wallpaper. So it gives you all the different type of wallpaper you can design on the plane that have symmetric patterns. Okay. So the method goes something like this. So let the first step, let gamma be a discrete subgroup. Of G. And we're going to consider two things. First, we're going to consider L, which is the intersection of gamma with the subgroup of translations. That's a subgroup of gamma because it's, right, gamma is a group, so it's and this is called the lattice or the additive subgroup of gamma. And then the second thing we're going to consider is the image gamma bar of gamma in O2, in the quotient, which we view as G modulo the normal subgroup R2. So this is not viewed as a subgroup. This is in the quotient group. Now that homomorphism will kill L. Right? The kernel of that homomorphism is the intersection of gamma with translation. So this is just gamma modulo its normal subgroup L. And out of those two pieces, we're going to assemble our discrete group gamma. Now our finite groups, if we had a finite group, then the finite group would be equal to its image in O2. And we would have classified it because we know all the finite subgroups of O2. Because finite groups contain no translations at all. So the new part of this theorem will be for groups where L is non-trivial, i.e. for this one over there. That one, here L. So here this would be equal to L. And gamma bar would be equal to 1. Because everything would be in the kernel of the map to O2. So this is sometimes called the additive part of the discrete group, and this would be the image of it, or the point stabilizer of it in O2. Okay, so I claim the first theorem. Let's first figure out what L can look like, and then we'll figure out what gamma bar can look like. First step. What are the possibilities for L? So I claim there are 3 possibilities for L, and that's it. Okay? One is that L can be 0. That's the case when gamma is finite. Two, the case we had here. L can be all integer multiples of a fixed vector, where b is non-zero in R2. All translates of a fixed vector. That certainly has the property that doesn't contain arbitrarily small translations. And the third possibility is that L can be all integer multiples of one vector plus all integer multiples of another vector where A and B are linearly independent over R in R2. Namely, where A and B give a basis. So there are only 3 possibilities for this lattice group. By the way, this case is usually called a lattice. So it's a group generated by translations in A and B, where A and B are linearly independent vectors. Okay, now I'm going to show you that those are the only 3 possibilities for L. So I claim, so let's make a couple of initial observations before we prove this. If you have 2 vectors in L, then B minus B prime is in L as a vector in R2. So the norm of B minus B prime is bigger than epsilon for some fixed epsilon. Well, that's because this says you have translation by B, you have translation by B prime. So this comes up because this is translation. This would be the vector of translation by T of B times T of B prime minus 1, which is T of B minus B prime. And all translations by our hypothesis in gamma have size at least epsilon. The norm of it is at least epsilon. So in other words, if you have 2 vectors in this subset of R2, they can't be too close to each other. Vectors can't get too close to each other. That's the essential observation. Okay. Now, so this condition is clear. We could certainly have gamma equal to 0. So assume L is not equal to 0. And so there are 2 possibilities. Case 2, so 1 is clear. You can certainly have L equals 0. 2, if L is not equal to 0 is the case where all vectors in L lie on a line. I mean, we don't know. I mean, either they lie on a line or they don't. And I mean, 0 is the simplest case. There they span a 0-dimensional space. Here they would all be vectors somewhere on a line. Okay? Now we let B be the vector on that line which is closest to the origin. Now that's not unique, by the way. But there has to be such a vector because we don't get vectors arbitrarily close to the origin. There must be one that's closest, because if I couldn't find one that was closest, I could find a sequence of vectors getting closer and closer and closer to the origin. But the origin is certainly in L. And vectors have to stay a bounded distance away from the origin. So there must be one that's closest. Now, I'm saying, so take B to be the closest one. But of course, that's not unique, because I could have, once I found B, I could have also found minus B, which is the same distance. but just choose one that's closest to the origin, then I claim that all vectors in L are just multiples of B. Namely, I'm in case 2. So this case arises if there's nothing in L. This case is what you get if everything is on a line. Okay, why is that? Well, this is our famous Euclidean algorithm argument. Suppose I had something else on L. Here's my B prime. And I write B prime as some multiple of B plus a remainder, R0 times B, where n is an integer, and R0 is some number between 0 and 1. Because I just keep marching out by multiples of B until I get one right before B prime, and then I have one after B prime. So B prime would be some 2 times B plus some multiple of B between 0 and 1. Now, if R0 is not equal to 0, then R0 times B is in L, because this is in L and this is in L, and it would be shorter than B. Right? Because R0 is of length less than 1. Consequently, R0 has to be equal to 0, which says that everything in the lattice is a multiple of B. Namely, the lattice is just integer multiples of B. So we've seen that Euclidean algorithm argument a couple of times for cyclic groups. Now comes the fun part. Now suppose that they're not all on a line. This is 3. In other words, L contains a basis of R2. There have to be 2 vectors in L, not both on the same line, so there is a basis. Okay. Now, take the basis, say A and B. So we want to organize ourselves correctly. So the first thing we do is we take the line spanned by B, and we let B be the shortest vector. We might as well insist that this is the shortest vector in L on the line RB. Why not? Replace it by another vector on the same line, which is in L if it isn't. And we might as well assume this is the shortest in L on the line RA. They're still linearly independent because we had the line spanned by B, we had the line spanned by A, and we just go to the shortest vector on each such line. And we're going to see if that gives us our generators that I want. All right, now before I go any further, I want to prove a little lemma that says if S is a bounded subset of R2, then the intersection of S with this subgroup L is finite. Well, if it were, this is just back to your course in calculus or topology. Here's our bounded set. Any bounded set could be put inside of a large ball, so it's enough to show that any large ball which intersects L is finite. Well, if it were infinite, you have an infinite number of elements in a bounded set. An infinite number of elements in a bounded set has a convergent subsequence, right? That's what we prove about compactness. So imagine that we have a convergent sequence of elements in L to this point, and subtract one of those elements, and you'd get a sequence of elements in L converging to the origin, because you can always translate by something there. And then you'd get arbitrarily small elements in L, which you're not allowed to do. Or in other words, we also showed that the distances, that this distance remains greater than or equal to epsilon for any 2 elements in L, so you couldn't have a convergent subsequence. proof, if infinite, can choose a convergent subsequence, but this is impossible as no sequence of elements in L is Cauchy. Right? Because the distances between elements can't get arbitrarily close. So this is an interesting combination of group theory and topology. So we're going to bear this lemma in mind. Now consider, we're still working on case 3 here, consider the parallelogram spanned by A and B. Here's the vector, I guess, A plus B. Let's call that parallelogram P. So we chose A, the shortest vector on its line, B, the shortest vector on its line, and then we take the parallelogram that they span. Here's 0. OK. Now the question is, are there any points in L on, let's see if I set this up right. I think I have it right. OK. Replace this parallelogram. There might be some vector inside the parallelogram that is closer to this line than the point B. Namely, there's some distance that B has from the line 0 to A. And there might be some point in the parallelogram intersect L that's closer to this line than B. So maybe there's a point here, B prime, or something of that nature, which is closer to A, to this line, than B. OK, there are only finitely many points of L inside of this parallelogram, because this parallelogram is a bounded set. So there are only finitely many possible points in L. So we look at all the points in L inside of this parallelogram, and we see if there are any of them that are closer to this line than the point B is. And we find a few, and we replace B now by the closest point. So replace B in L by the point in P, which is P intersect L, closest to the line spanned by A, but not on it. Maybe there are no points that are closer than B. But if there are any points in P closer to B, replace B by that point, and we have two new points. And we take a new parallelogram now spanned by those two things. So we started with our parallelogram spanned by A and B, but we might have found a point inside that was a little bit better for our usage than the point B. So now we replace the parallelogram by this, where now this is certainly the closest point, because this parallelogram was contained in the other one. This is the point in the parallelogram closest to this line A. OK? Now I claim that there are no other points in this parallelogram as close to this line A as the point B. Because there are no points inside the parallelogram. We certainly know that. Now, there might be a point that we thought was as close that lay on this line. Or there might be a point that we thought was as close that was on somewhere on this line. But if there were a point that were closer on this line, then by subtracting the vector A from it, we would have found a point that was closer to this line than B, because it was here. So there can't be any points on this line. And all these points on this line are exactly as far from the line A as B is. So there are no such points on that line. So now we know that in the entire closure of the parallelogram, B is the closest point to this line here. And now the claim is that L is generated by multiples of A and multiples of b. So after these adjustments, and these adjustments are necessary. Here, we had to make an adjustment where we replaced our vector on the line by the closest vector to 0. Here, we initially made an adjustment that we took the shortest vectors on the line, but then we still may have to have made an adjustment because we may have taken the wrong 2 lines to begin with. See, we wouldn't want to have started with these 2 lines because there were vectors on this line. So we found that vector by taking the closest vector inside the parallelogram of our initial choice. And then the claim is that everything is spanned by A and B. And here's the proof. Any vector v in R2 is a real combination of A and B. Right? Where R and S are real numbers because A and B give a basis. Just like any point on this line was a real multiple of B. And now I write it as an integer times A plus R0 times A plus an integer times B plus S0 times B, where this is an integer, and this is some number between 0 and 1, and this is an integer, and this is some number, S0 is some number between 0 and 1. And if this vector is in L, then if I subtract n times A and m times B, I get another vector in L, because A and B are in L, so any multiple of A plus any multiple of B is in L. And that implies that R0A plus S0B is in L. Okay? But this is a vector in the parallelogram, because the parallelogram is exactly the multiples of A plus the multiples of V, with the multiples being less than or equal to 1. This is the vector A plus B. And everything here is just some multiple of A plus some multiple of B, where the multiples are less than or equal to 1. And since we've identified that B is the vector in the parallelogram closest to A, there can't be any other intersections inside that parallelogram, so this vector is 0. And consequently, our vector, which was in the lattice, was a multiple of A plus a multiple of B. So this is a good argument to go over. We've constructed a region in the plane that has only its vertices or its intersection with L. So P intersect L is then just the set 0, A, B, A plus B. And therefore, it cannot contain any vector of this form where both R0 and S0 are less than 1, except when both R0 and S0 are equal to 0, in which case the vector was originally a multiple of A and a multiple of B. OK, so we've gotten somewhere. We've showed that if I have a discrete subgroup of the motion group and I look at its translations, it either has no translations, it has translations by one fixed vector and its multiples, or it has translations by 2 fixed vectors, A and B, and all of its multiples. So you'd have translation by A, you'd have translation by 2A, you'd have translation by 3A, you'd have translation by B, you'd have translation by 2B, you'd have translation by A plus B, you'd have translation by 2A plus B, you'd have translation by A plus 2B, etc. But still, those translations do not get too close to each other. If you tried to add one more translation anywhere else other than the multiples of A and B, you'd be able to get an arbitrarily small translation. That's what we're saying. OK. Now, surprisingly, this stuff, which looks like, oh, well, we've just done the translations, well, we're almost done. Because now we consider the image gamma bar of gamma in O2. And here's the key lemma that we're going to use here. Gamma bar preserves the subgroup L in O2. Preserves. So namely, if I view gamma bar as acting on 2 space via its realization as orthogonal transformations, it takes this lattice, or whatever it is, to itself. That's not saying much if the lattice is just a 0 point. because any group would take the lattice to itself. But if the lattice is generated by one element, or even stronger, if the lattice is generated by two elements, that's going to be a very strong statement. And here's the proof. Say B is in L, i.e., translations by B is an element in gamma. Okay. Say gamma bar is in gamma bar, and lift it to an element A in O2. So in other words, O2 inside of G. So O2, the quotient group, actually you can think of it as a subgroup of G. So there's an element in this O2 that maps to this gamma bar in gamma. All right, then, actually, lift it to an element. This isn't the right way to say it. Lift it to an element gamma in the subgroup gamma. There we go. So find an element in gamma, that maps to this element in O2. And consider gamma TB gamma inverse. So that's a conjugate element of this translation. So it's another translation. This is an element in gamma because it's the product of three elements in gamma. This element, and the inverse of this element. And our general formula for conjugation shows that this is translation by gamma bar of B. Namely, this is T of gamma bar of B. So we've just shown that if B is an element of the lattice, so this translation is in gamma, then this translation is in gamma, which implies that gamma bar of B is in the lattice, which is the saying that the elements in gamma bar preserve the subgroup L via this conjugation formula. Okay, now that is very strong. That's very strong because I'm now going to show you how much restriction that puts on gamma bar. If L is 0, it means nothing. Then we know gamma bar is either Cn or D2n for any n greater or equal to 1, because we can have any of these as finite groups. But suppose we're in the other extreme case. We're in case 3, where L is Za plus Zb, A and B are independent. We know that gamma bar has this form, but can we get any cyclic or any dihedral group? I claim gamma bar is equal to Cn or Dn, D2n, with n equal to 1, 2, 3, 4, or 6. That's it. So that when you get a large translation group in your discrete subgroup, the image, which is a finite subgroup of the orthogonal group, because it has to stabilize this subgroup, is very restricted. In particular, it has order less than or equal to 12. Because the biggest it could be was if n is equal to 6 in the dihedral group of order 12. So this is really quite surprising, no matter what A and B are. And in fact, if we're going to get any of these cases, A and B are going to have to have a very special relationship to each other. So in the general case, we're only going to get n equal 1 or 2. Okay, so I'm now going to prove this to you. Okay, remember we had this group G, and it contained a normal subgroup R2. And when you made the quotient, it was isomorphic to this group O2 of the rotations. So if we have a subgroup of G, we can follow the image. G maps via homomorphism to this quotient. So you can take the elements in gamma and apply the homomorphism, and then you get a subgroup of this quotient group. That's called gamma bar. It's the elements in gamma if you forget their translation part. It's what are the possible rotation parts of an element in gamma. Okay? So to say that it preserves the subgroup L means that the miraculous thing is that this quotient group still acts on 2 space. And in its action on 2 space, it has to preserve the sub-things in gamma that are translations. And that's via this conjugation formula. That when you conjugate a translation by B, by an element in O2, you get a translation by that. So you have to actually do that. That's this, remember that, well, let's just do it. If it makes you feel better, I still have time, I think, to prove this thing. I'm going to wave my hands at it anyhow. Let's see this formula. So gamma of a vector v is, say, A times AV, right? And TB of a vector w is w plus b, right? And then gamma inverse of a vector v would be A inverse of v. Okay? Now let's calculate what we get when we apply this product of elements in the group to the vector v. Sorry for this deviation. So if I do gamma inverse of v, so I want gamma tb, gamma inverse of a vector v. So it's gamma tb of A inverse v, right? Which is gamma of A inverse of v plus b, right? Which is A of A inverse of v plus b, which is v plus A of b. So that this has the property of taking a vector and translating it by the vector A of b, where this means apply this orthogonal transformation to the vector v. So that's what I mean here. Translation by this orthogonal transformation of b. And since this conjugation preserves gamma, this new translation that we get has to be in gamma. So it is in L, which is the intersection of gamma with R2. So far, so good? Now, let's just see why n is so incredibly restricted here. Well, I'll give you my favorite argument, which is a little different than Artin, and next time we'll start with Artin's argument. Suppose I have an element, A, in gamma bar, and suppose it's a rotation. I have to show that the order of A is equal to 1, 2, 3, 4, or 6. Because you can determine which dihedral group you have by which rotations you have in it. Okay? If I had any other dihedral groups, I'd have other orders of rotations. Okay. Now consider the characteristic polynomial of A. It looks like this, I claim. X squared minus the trace of A times x plus 1. It's a two-dimensional transformation. And if I have a rotation by the angle theta, and theta is equal to e to the 2 pi over n, that's my first rotation, that's the rotation that I'm looking at, then this trace, if I call this complex number z, this trace is the number z plus z bar. Right? Okay? Now, that's what it looks like in general. This is some real number. And I also happen to know, so let's write it as x squared minus tx plus 1. I also happen to know that t squared minus 4 is a negative number. T squared minus 4 has to be a negative number because the roots of this quadratic polynomial are two complex conjugate numbers. They're not real numbers. And so by the quadratic formula, if you have a quadratic equation, its roots will be imaginary, provided its discriminant, b squared minus 4ac, which in this case is t squared minus 4, is negative. Actually, I could have a rotation by order 1, so I should put this because, I could possibly have z is equal to 1, or I could possibly have z is equal to minus 1. Those are the only possible real roots of this polynomial, and that would be when t is 2 or minus 2. But I have this inequality for the trace. On the other hand, because A stabilizes this lattice, I claim that the trace is an integer. Because consider the matrix of A with respect to this basis of R2. Because matrix of A with respect to the basis AB has integer entries. Because it preserves this lattice. So if you ask what the transformation A does to A, it takes it to an integer multiple of A plus an integer multiple of B. That's the first column. And if it asks what does it do to B, it takes it to an integer multiple of A plus an integer multiple of B. That's this amazing thing about it preserving this subgroup. So if you have a matrix with integer entries, its trace is an integer, right? Because the trace is the sum of the diagonal entries. Okay. Well, if the trace is an integer and t squared minus 4 is less than or equal to 0, that does not give too many possibilities for t. T can be equal to plus or minus 2, plus or minus 1, or 0. That's it. Plus or minus 2, those are the transformations of order 1 and 2. Plus or minus 1, those are the rotations of order 3 and 6. And 0, that's the rotation of order 4. That's it. So you see this wonderful stuff that starts to occur when you do discrete groups. You have two things. You have all the arithmetic, something has to be an integer because it preserves a lattice. And on the other hand, you have something has to be bounded as a real number because the roots of these things were complex. And you put those two things together, you get a very small list. Integer plus in a bounded interval. There are only finitely many. Likewise, we did this. The same argument was this L intersect S is finite. That was by topology and arithmetic. So that's why discrete groups become such an interesting subject in mathematics. They combine what you know from calculus and what you know from algebra. It's not just one subject. We're using things about the real numbers. Like this doesn't make much sense in algebra. There is no less than or equal to in algebra, but there is in the real numbers. And this doesn't make much sense in calculus. Integers are no different from 2.000000001. But it makes sense in algebra. So this shows that the rotations in this group are very seriously restricted whenever we have these two independent generators. And next time I'll finish up the classification based on that. Artin has a different proof of the fact that the order is less than or equal to 6 based on the shortest element in the lattice. But I thought I'd show you a number theorist proof. Okay, have a good weekend. See you Monday.